So thank you to the organizers for putting together such a wonderful workshop until today, I guess. And so I'm going to try my best to contribute to it as well. The paper that I want to present today is joint work with Alessandro Bonatti from MIT and Alex Smolin, who is a graduate student who is finishing his PhD this year at Yale. The title, Selling Experiments, refers to experiments in the sense of Blackwell. That is, we want to think about providing statistical information in the sense of experiments as Blackwell formulated it. And what we're interested in particular is how to package information and how to price information. Okay. We think about basically a problem between two sides, the data seller who wants to offer his data that he has available to a data buyer who's really your standard Bayesian decision maker who faces a problem of a decision process under uncertainty, and he goes into this decision already with some partial information that might inform him, but there's always a possibility of acquiring some additional information, thus augmenting his own private information so as to make an even better and informed decision. And from the data seller's point of view, the question is, how do I want to provide this additional information? At what price do I want to provide it? And given that the data buyers come in with their own luggage in some sense, their own history, their own information, the question is whether I want to provide different pieces of information to different buyers. And given that I'm providing different information, do I possibly want to offer it at different prices across a variety of possible buyers? Okay? And so the leading example that helped Alessandro and me was to think about it, but also to motivate the question, is simply, how do I provide access to large databases as they are prevalent on the internet? So think about data brokers such as Axiom and BlueKai, but also Google in AdExchange, basically providing information for advertisers in terms of narrowing, framing, fragmenting large parts of their own proprietary database. Okay. Perhaps sort of a specific example to keep in mind throughout the talk, think about behavioral retargeting, right? So here the idea is that firms want to basically want to provide tailored advertising to customers that actually have been on their website before. So that's why it's retargeting. Clearly, advertisers have already some information about the characteristics, the attribute of the consumer that they're facing. But in order to know how far they should go and how specific the advertising should be, it probably helps them to acquire some additional information, third-party information, from one of these large databases. Okay. How valuable that information is, of course, will depend on how good their own database is, how much information they already know about the consumer. We're going to think about the data seller as providing an information product. Okay, that's really sort of an experiment in the sense of Blackwell. And what it will do is to basically augment the information that the decision maker already has with further additional information, incremental information about the pair of relevant state. The issue here is that the value that that experiment provides to the decision maker will, of course, depend on his own information, that is, to what extent he's already informed about the decision that he has to make. Okay? And to the extent that that is his private information, the question is, how can I elicit that information? How can I find the right match between the incremental information that the data seller can offer and the information that the data buyer already possesses? Okay. Okay, so now you see that we'll go basically a little bit in the direction of trying to find an optimal price, find the optimal match in terms of the product, and eliciting the private information, so the language that should be familiar to you in terms of mechanism design. So what we're trying to do is to think about how to design information in terms of what's the nature of the experiments that we want to provide, and then second, how should we price individual experiments, individual accesses to the database. Okay. Sort of the take that we're going to have here is that the seller can really just contract on the information that he's provided. He cannot contract or ask for commissions on the eventual action that the data buyer purchases. Okay, so that's a little different, if you wish, from auction for sponsored search, where I'm basically providing information as well as a product. Here we're simply setting just the information product itself. Okay. And so some of the results, we're going to show that it will be optimal to basically offer, from the data seller's point of view, a menu that is a whole class of experiments. And then we're going to try to characterize what these experiments look like. Okay. The two main results that I want to show today is that, first of all, experiments will be, or the items on the menu, that is the experiments, are going to be simple in a sense that they will only use a limited signal space. But then also the menu itself, that is the collection of experiments that we're going to offer, is going to be coarse in the sense that it's going to be a much smaller cardinality, as would be indicated by the diversity or the heterogeneity in terms of the bias. Okay. And then I'd probably have a little bit of time to think about what are the distortions information and how do we screen different buyers by means of matching their prior information with augmenting information, and sort of that will be directional information. Mm-hmm.
Just to get some intuition, so if the data buyers, if all the different types want totally different things, now I can completely price discriminate them by giving them just the information that they need, which would be useless to the other ones, which would seem to go against this intuition that you would have, or this statement that you would have very few items on the menu.
Mm-hmm. Mm-hmm. Very good. So the piece I think that you're referring to, Vince, is the interaction among the buyers of the information. Okay, we're not going to look at any interaction after the acquisition of information. We can please think of one particular buyer wanting information for a particular decision problem. Where the interaction is going to come from is that different buyers have different quality of private information already, and to the extent that I have better private information already, I'm less willing to pay for the additional information provided. Okay. Clearly, from the point of view of the data seller, the data buyer who is ignorant or uninformed is sort of the best buyer because he has the highest value to the experiment. Everybody else will have a lower value of the experiment. So what I'm going to try to do is to screen, to separate in some sense buyers who already have a lot of information from those who have very little information.
So will that be single dimensional?
No, you will see information is typically very high dimensional. Okay. This is really not to document my knowledge, but rather my ignorance, in the sense that I think there's sort of a lot of questions surrounding information, the value of information, how to think about the value of databases and so on. And I would like to learn more, especially on what's been done in that respect in computer science and theoretical computer science, and I couldn't find very much. So this is really just sort of a sample of the literature in economics. Okay, so let me describe you the model, which is going to be fairly standard. We think about the single decision maker, that's a data buyer. There are going to be a finite set of states of the world, a finite set of actions, and the state, together with the action that the decision maker is going to take, is determining his utility ex post. Okay? The leading example that I will throughout the talk is a particular simple one where the objective for the decision maker is really to matching the action to the state. Okay? If I match the action with the state, so simply think of action state space basically of the same cardinality labeled according to the same indices, then I get a payoff of 1. If I fail to match with my action the state, simply because I don't have enough information, I got unlucky, then I have a payoff of 0. Okay? The generalizations you will see won't require much work, but the formulas are going to be particularly easy and transparent if I'm going to stay with this matching action and state formulation. Okay. So this is probably way too much notation, but all I want to say is that, yes?
Space and state, these are different, but you want to match the state.
simply, this is the general setup. We want to just label the actions from 1 to n, label these states from 1 to n, and what the decision maker is to choose. If he were to know the state omega 1, he should choose A1 when the state is omega 1, A2 when the state is omega 2. These are just a generic description of action and state. So,
but we should assume they're equal.
You can assume they're equal, exactly. Yeah. Right. So that for the example and for the calculations that you will see. Yeah. Okay. Right. So we want to start basically with a Bayesian framework that we say the states have some distribution. That's what we refer to as a common prior. But the decision maker, when he makes this decision, may have some prior information. Let's call this his initial belief or his interim belief that is being generated through some signal process. So what is important here is that basically the initial belief that each individual decision maker has when he comes into the process is informed by the signal R, and that leads him to adopt an interim belief over the possible states of the world. Okay, that's how he enters this decision problem. Okay, from the point of view of the data seller, the database, this problem presents itself that there's a distribution of buyers in the world who have a distribution of possible beliefs that's given by f of theta. Okay, so the data seller doesn't know what the belief of a particular data buyer is, how much information he has already, but he has the statistical information given by that belief f of theta, which is induced by the prior and by the nature of the initial signal structure. Okay. And the additional information that he can provide has precisely the same structure as initial signal, in the sense that an experiment, so that's the formal definition that we're going to adopt here, an experiment which consists of a signal space, capital S, and a likelihood function pi, is simply mapping that generates, as a function of the true state, a probability distribution over the signals. Okay? And we're going to assume that the generation of the type and the information structure is conditionally independent, so that the joint distribution basically is just a product of the marginals. Mm-hmm.
Do you allow for signals to be correlated with valuation?
Absolutely.
On the previous slide.
Oh, absolutely. Right? Again, the initial signal is a mapping from the state into the signal space. So that's the sense in which this is prior information, otherwise it wouldn't make sense, right?
Question?
Mm-hmm.
So f of theta is before you condition on S, or is it after?
It's before you condition on S, right? So you know that in the market there are data buyers who have varying degrees of private information that's described by f of theta. Okay. And so from the point of view of the data seller, the choices that he is now offering is basically a set of possible experiments. That's a menu. So script I is basically a set of possible information structures or experiments. And a particular experiment is simply capital I. And each one of these experiments is offered at the price T. Okay. So so important, we are not allowed to contract either on the action or on the final realization of the space. So typical scoring rules, the belief elicitation, are simply not available. We can simply price the information or price the experiment. Okay. So the timing is the following one: the type of the decision maker is realized, so his interim information. He then can make a choice out of this menu of experiments. For every experiment that he's purchasing, he has to pay a price. And after he chose the experiment, he's simply going to observe a signal realization. Mm-hmm.
Is the information provider unconstrained in what types of signals he can generate? Or
yes.
Does he have an initial signal and he can only garble that?
For all that we do today, we basically have him. So think about this completely unconstrained. So he can condition on omega. So think basically there is this large database that is pre-installed. There's no cost of either having or not providing the information. I'm just simply choosing how to, okay? Right, so I don't have time for the interpretation, but just to make, okay, good. So, so how should we think about this? From the point of view of the decision maker, if he were to make a decision just on the basis of his partial information, his interim information, all he could do is to form a conditioning given his initial type theta, and he would then choose the best action that would maximize his expected utility. Okay? Now, if he's being provided with an experiment, okay, then he realizes that he can do better than what he could do without the experiment. Okay? And how can he do better? Well, besides conditioning on the theta, he can also condition on the signal. Okay? And the difference, and after taking the expectation to get the expected value of the experiment from his point of view, and the difference between these two is simply the value of the experiment from the point of view of the decision maker. And that is what is he willing to pay, in some sense, to have access to that additional information.
It's not negative, right?
This is not negative, absolutely, right? Because I can always discard the additional information and just do, right, so.
We kind of assume that one of the menu items is to pay nothing for nothing.
Right. No, it's just the value.
For the sorry, and remember here we haven't yet had any prices, so this is really just the gross value of the experiment provided. Yeah, and that is not negative. Okay. Good. So, just to have a little bit of a handle on what it is that we're talking about, the interim probability is basically just a belief about any particular state realization. The experiment is really just a likelihood function that tells me, given the true state, what's the likelihood that a particular signal is realized. And so therefore we can think about a particular experiment simply as a matrix pi that conditional on the state omega, so that's the rho, generates different signals. Okay. Specific interests, specific experiments that we'll refer to and that will be of use. One is locally and noise-free. One is the one where we basically provide with the signal Sj just information about one state. So that means there's no noise in the signal. Once that signal is received, I know that the true state is I. Right? If you look at the entries from the row side, then if it's just zeros with the exception of 1, 1, then we refer to this as locally non-dispersed, because it basically means that the information that we provide about omega I is non-dispersed, it's concentrated just on one signal. Okay. And of course a perfectly informative experiment is one that has just ones on the diagonal and 0 off the diagonal. So that's one that is globally noise-free and non-dispersed. Okay. So here's why you see it now, why it's a little bit helpful or useful to, in the presentation, focus on the matching action and state, because given that we have that assumption that it's the payoffs are either 1 or 0, we can really describe the value of the experiment in a very compact form. That is, I'm simply going to think for every signal that I observe, so these are the J's, I'm going to choose that action that has the highest posterior likelihood, and the posterior likelihood is simply the prior times the likelihood, right? And I'm going to do this for every signal. And of course, there's a probability of signals, but in the Bayesian framework, it all cancels out. So this is really the value of the experiment. And to the right is what I would do in the absence of the experiment. In the absence of additional information, I would simply choose that state that has the highest prior probability, and the difference is simply the value of the experiment. So, what are we talking about, therefore? The allocation problem that we're interested in is the one where we provide a random allocation because the signals are random, right? And in fact, the valuable allocations have to be random because they want to be tailored to the state, okay? And the agent is essentially one that has unit demand because he's to choose one out of the n actions, okay? So that's a problem that we're looking at, okay?
So should I understand this matching experiment as providing a basis for computing more general utilities?
Absolutely. All that would happen here is you would multiply this instead of 1 with the utility differences from switching action. So that it would all go through. It's just then a much more elaborate formulation. Okay. So Just to get a little bit of geometry, if I'm starting out with a posterior belief in a 3-state space, so theta 1, theta 2, and 1 minus that, as the interim belief, then I can ask myself, what is the value of a perfectly experiment? And that's basically a mountain with 3 faces. The edges represent the fact that we are switching, given the prior or the interim belief, we would switch the action to one that is more appropriate. And clearly the most value is being attached by that person who has the least informed prior or interim belief. Okay. So here's the formal problem that we therefore set out. We want to offer a menu of experiments. We're going to look at a direct mechanism. And really what we want to do is to maximize the revenue from the seller's point of view, the revenue for the database, so you don't see any cost of providing information here. And the 2 things I need to be worrying about is that I want to get incentive compatibility, so that when I'm type theta, I'm not trying to get an experiment that's meant for somebody else. And I also have to satisfy participation constraints so that the net value after paying for that information structure has a value larger than 0. Okay. So let's dive right in, get sort of a few results. Right, so we have, think about it, even though we have just a finite state of the world, the beliefs are basically a continuum, right? Because these are the beliefs about that I have about state 1, state 2, and so on. And from the states, I'm going to generate signals, I'm going to take action, so that's potentially complicated. The first thing to cut this through is to say, well, actually, an optimal experiment will never have to have more signals than the action to take. Because after all, what is the signal? It's really providing me with a recommendation of to choose an optimal action. Okay? And therefore, I can always reduce the dimensionality of the signal space down to the action space. In fact, typically that will improve the value that I'm providing, because if I provide more signals, then these are basically more opportunities to deviate. And so if I'm compactifying it in a sense that for the truth-telling person, I'm going to combine all signals that will lead to the same action anyway, then I'm keeping his utility constant, but the misreporting utility necessarily has to go down because I'm removing options. Okay? Right. Yeah?
So I'm a little surprised because you'd need to make an action recommendation for every different type of the...
Yes. Right.
Why is it the cardinality of actions rather than actions cross types?
Remember, I'm talking here of every experiment, right? Right. So every type is going to choose just one experiment, and for that experiment. Yeah. So with that, just to give you an illustration, right? So if you go now to the binary state binary action case, where the utility function is simply that, the first proposition allows us to basically look now also just as binary information structures, okay? And without loss of generality, we can think about the diagonals here as being larger than 1, so that we sort signal belonging to state, yes? And now we want to know, how do we choose that information structure? Mm-hmm.
Intuition for this proposition, simply you should just give the action recommendation to the buyer, because if you tell him more information, that could only...
That's exact. So it's not a difficult result. That's sort of a result that is in the Bayesian persuasion literature as well, right? That's the minimal information I need in order to choose the right action, and there's no reason to give more information than that.
Mm-hmm. So I understand the intuition. If each different type is choosing a different experiment from my menu, then I certainly understand the intuition that there should only be, at most, a number of action, cardinality of signal space. Mm-hmm. But I thought you said that that we were going to end up with a much coarser set of experiments.
Yes.
So many types are going to be choosing the same experiment.
Yes, and so that proposition doesn't address that yet at all.
Okay.
Right? Because we're just saying about every single experiment. So wait a little, okay? So this is an information structure now, right? So we can ask in this little information structure, what is a locally non-dispersed and what is a locally noise-free information structure. This information structure has the property that it's both, okay? And let's just pause for a moment and see what this information structure does do. It basically gives me noise-free information on the high signal because it tells me without doubt I'm in the high state, whereas here clearly I have noisy information. Okay. But what is important is that that particular information structure, while it does look informative, is actually valuable only for that agent who assigns a high probability to omega L. Because in the absence of information, he would have chosen the action that is relevant for omega L. Okay. Now he has sort of clear evidence that against his prior, he actually has sometimes a reason to choose the action that is relevant for the high state. Where somebody who had assigned a high probability to the high state, okay, would find this experiment completely without value, because under both signal realization he would still stay with this commitment to the high action. Okay, so that means that the value of information from a particular experiment differs across different bias. Okay? And in some sense this is just a reflection of the fact that the ordering that Blackwell suggested is highly incomplete. Okay? And we're using this incompleteness of the ordering here to basically screen bias according to their willingness to pay, because they rank information differently. And that allows us to actually screen them. Okay? So here's just a plot of the binary state. Okay? So we come in with the prior probability theta about the probability being that the state is high. And I'm going to provide a perfectly informative signal that has entries 1 on the diagonal, and I'm asking myself, what is the value of that experiment? Okay. So clearly, it is very high for the uninformed guy, which has a split prior, and then it's declining in both directions. Okay.
You should not. I think you should normally type 2 and alpha and beta are an error probabilities, not a normal probability. So I would use the
different labels. Yes, thank you.
The common in statistics you use exactly the opposite, that alpha and beta are the
Not only do I show my ignorance in computer science, but also in statistics. Thank you, Bernard. That was very subtle. Okay, I'm happy. Okay, but what I do want to point out, even sticking with the alphas and betas. So here we have now an experiment that is not perfectly informative, okay? And what you see here is that the value of the experiment on both sides of 1/2 is different, okay? This is an experiment that is valuable for the low types, so low signals, low probabilities on the high state, but not so valuable on the right-hand side. So what we immediately see is that just the distance from being uninformed is not a sufficient statistic anymore. It's not sufficient information to evaluate the value of experiment, and there's sort of an indication of the incompleteness of the ranking. Okay, that we're going to make use of. Okay. But I guess I want to at least use sort of geometry here to make 2 additional points. If you think now about, even here already, this as an incentive problem, you'll notice that there are quite a few things different from a standard problem, okay, in the sense that the highest type is actually the interior rather than the boundary. Okay. Incentive constraints run down locally to the left and to the right. Okay. And participation constraints are not just on one side of the mechanism, but also on the other side. Okay, so this is as a mechanism design problem, it's sort of unusual in a sense that it's not just a local incentive constraint, it's not just local participation constraint that bind. Okay. And it's also evidence in some sense of the high dimensionality of information, namely given that really our prior varies just in the 1 dimension. There is differentiation provided by the information both horizontally as well as vertically, and we can't separate these 2. Okay, they basically come through Bayes' law automatically, both in a horizontal and a vertical differentiation. Okay. Let me just give you a little bit of a sense of general results, but staying illustratively with the binary state. Okay, so with a binary state, we can really express everything in terms of the prior and the informativeness of the information structure. And so we can think about beta here as the baseline informativeness and alpha minus beta of the relative informativeness between one of the two signals, okay? So that we can plot the feasible set of experiments as follows, and we can ask, given what the value of the experiment is, what are the indifference curve, what are the directions in which I would like to improve the value, okay? And the important point here is that if I keep the relative informativeness constant and just increase the baseline informativeness of the experiment, then actually we see an increase in the utility across all types. Okay? So that means optimal information structure is necessarily going to force us onto the boundary here. Okay? Which basically means that we know, even though we haven't yet determined where on the boundary we're going to be for different types, we're definitely going to be at the boundary. Okay? And boundary here in terms of alpha and beta simply meant that we're going to provide non-dispersed information structures. Okay? And so this is indeed the sort of the main characterization for finitely many states in action and allowing for continuum of types in terms of the beliefs. And that says, first, we're always going to offer the fully informative experiment, that is the one that has diagonals, that's always going to be part of the optimal menu, okay? But then any other experiment, okay, will have to have the feature that it's locally non-dispersed. Okay, that is, there will be at least one row there that has just zeros and 1, okay? And that's basically all that can be said about the case of the general setup. Okay. And the additional result in terms of the yeah. Mm-hmm.
General result including sort of general utility functions? Or?
Exactly. So nothing would change. Exactly. Yeah. Because it's this drive towards the boundary and to the maximal separation that gets you this locally non-dispersedness, but it doesn't get you more than that.
What is the meaning of the after the 2?
Oh, basically now we have sort of a few options that we can do. Okay, that is, I can try to develop a little bit of the intuition by choosing simpler example and give you sort of partial results or sort of more complete sort of characterizations and more exact solutions. Okay.
So I have a couple of questions. So here you're assuming that after the mechanism is run, there's no sharing of information across buyers?
No, there's just a single buyer, but there are instances of that buyer in terms of different types. Okay, so there's no interaction of the buyers afterwards at all. So that's an interesting direction, of course, to think about. Yeah.
Question. So here you're also assuming that the utility function, so the buyer has a single utility function. You're not considering the case where there's where the buyer is drawn from a population where different people might have different utility?
No. So the only heterogeneity that comes in here is from the heterogeneity induced through information, absolutely. And so...
In statistics, normally, if I...
Who invited him?
You get the measurement result, for example, and then you have to trade off one error against the others.
Yes.
And so normally they are on a curve. So alpha and beta are not independent. They are on a curve, and that's the quality of the experiment, so to speak, how close it is to revealing. So normally you can say you can only, trade one or off one, given one experiment, an error after the other. So I wonder whether this interdependency of alpha and beta is here in your model.
Yes. So no. Okay. So what I thought you were going to go, how do I choose the errors, that is, in some sense, type 1 error versus type 2 error? Exactly. In the experiment, since it's an experiment in the sense of Blackwell, we don't face any constraints in terms of choosing the alphas and betas, apart from they're being well defined. Okay. But it is a choice of how do I want to place type 1 and type 2 errors. Okay. And so that's what I maybe sort of the second to last results that I want to show. So let me stay for the moment with just binary states. Okay, so there are just two types of possible bias, theta L and theta low, but there are many states and many actions. Okay, so that information could lead me to take one out of n possible actions. And let me now order the states by their ranking in terms of the likelihood ratios. Okay, so I'm simply having the two types. There are some states that are deemed more likely by the high type, okay, and there are some states that are deemed more likely by the low type, and I can rank them. Okay, and now I'm going to ask essentially how do I use that ranking of the initial priors in order to provide information. Okay, and so the result that falls then is then that we have two types. So one type is going to get full information, the perfect experiment. The other one is getting to have a noisy experiment. Okay, and the noisy experiment is going to have the structure that it's not going to provide him with any information about the lower states which he deemed unlikely, and is going to provide him with non-dispersed information on the states that he deems more likely. Okay, we're filling in the noise. Okay, we're filling in noise so as to basically have the other type not want to choose that experiment, because for the other type he deems these states not very likely, and therefore this information structure would leave him very confused as to what the optimal experiment is. Okay, so in other words, in terms of incentive constraint, what this does do is it minimizes the type 1 error that the agent incurs that chooses that experiment. Okay, and it maximizes the type 2 error that the other type would face if he were to try to acquire that experiment. And so that's a sense in which type 1 and type 2 errors show up here now through the incentive constraints that we're providing. Okay.
So just going back to Nick's question, so it looks like you're giving the same menu of experiments to all the types. So why is
Absolutely.
So why is it enough to have the same number of signals as the number of actions available?
Because all the types have the same set of actions available. Yeah. I mean, I could extend it and then...
I mean, it's not that I'm just going to play the action that you tell me to play. Like if I have a one-to-one mapping between the signals and actions, it's not that every type will want to just play the action.
No, that signal will have different content for different types. Okay, it will have different content, but they will know how to interpret it. At the end of the day, all they want to do is to choose one out of the n actions, and that's sort of the reason that there's this natural cardinality restriction, or natural minimal cardinality. Let me just conclude with one last, okay? And so now I want to basically give you the coarseness result, that is to say that the experiment is simple in the sense that it has a minimal cardinality, but also the menu is coarse relative to the set of choices available, relatively to the diversity in the types. Okay, and for that we're going to return to the binary states, but allow a continuum of types. Okay, so we could possibly now offer a continuum of experiments. Okay. And the answer, and what we're going to see is that actually the optimal experiment, the optimal menu, is going to have at most 2 experiments. So it's going to be very coarse. Okay. Right, and so, yep.
We have only 2 types now?
We have 2 states. Okay, it's a high state or low state. Therefore, we think about at most 2 actions that are relevant. But the types are now on a continuum between 0 and 1, which are simply my prior belief that the state is high. Okay. So we're going to try to argue that the optimal mechanism is to offer at most 2 experiments in the menu. Okay, and what I want to indicate here is that, remember we before had the triangle that we were thinking about the highest type in the middle and then all the other types to the left and to the right. Well, actually, that's precisely the picture also that arises when you think about incentive compatibility. Okay. the net utility information and that we have to give the high type has to be incentive compatible with the utility that we give to locally the types below him. Okay? But below him, we can approach him from the left as well as from the right. So that means we're going to face a constraint now that says locally the incentive constraints have to add up to the same thing when we come from to left to the right. Okay? So therefore, we basically have a necessary condition, okay, that says if the allocation queue is implementable and responsive, is basically was simply a condition that says that guarantees that the participation constraint at the low end at -1 and at +1 are satisfied. Then it ought to be the case that this Q, which is simply difference alpha minus beta, is non-decreasing, okay? But that the new condition here, this is the integral conditions, which comes from the fact that the local incentive constraints have to be matched, is basically giving us this integral condition that the sum from 0 to 1 has to add up to 0, right? So that basically they have to converge to the same indirect utility of the mid-type, okay? With that, we have sort of a linear problem in terms of the virtual utility, okay? And absent this integral constraint, we would simply have an all or nothing information structure. This is either we provide full information, perfect information, or zero information, okay? But because of that integral constraint, we now have to also allow for intermediate. That forces us basically to choose exactly one intermediate solution, okay? And so that's the result now, that an optimal menu consists of at most 2 experiments. We will always provide the efficient experiment, the fully informative one. But then the second experiment is one in which information is degraded and is both locally non-dispersed and locally noise-free. Okay, and so that's the sense in which we're going to provide a coarse menu, because even though we have a continuum of types in terms of the prior belief, we are only optimally offering only 2 choices. Okay. And so you could ask yourself, when is it the case that I really want to use 2, and when is it the case that I'm going to only provide 1? Well, if you have a symmetric distribution around 1/2, then basically this adding up constraint is automatically satisfied, and therefore we are basically in a situation where the integral constraint is always satisfied, and then we're only going to sell the most efficient experiment, but otherwise we're going to use further versioning of the experiment. And then, in fact, it doesn't need to be the case that the highest type, sort of a classic result in the mechanism design literature, get the efficient allocation. No, that depends now on the distribution of prior information in the population. It could very well be that we bias it away. Okay. And so the last sort of open question that we're working on at the moment is to think about whether this result, this coarseness result that we have proven for the binary state but the continuums type, we believe that that's true also for the finite state and finite action version, basically by sort of a bundling argument. But since the potential set of experiments is quite rich, this seems to be a more difficult problem than we initially thought it would be. Okay. So basically I wanted to give you a first way to think about how we should package information, how we should price information. It was really in a very stark model where there was no further interaction among the buyers of information, and as the many questions in the audience pointed out already, that clearly sort of an interesting version to think about it. Advertisers, financial decision makers, when they acquire information, clearly are aware of the fact that that information might also have been accessed or used in one form or the other by competing decision makers, and the question to what extent that will influence the way I want to sell information, how I want to package information, is sort of an interesting and open problem. Okay. Ilya?
You have used the anywhere and the somehow the buyer's initial types come from some common prior and
of, as opposed to just having some heterogeneous prior beliefs?
No, actually, so you're right. For the first result that you saw, the non-dispersants, we don't need that. When we then want to derive what is the actual structure of the optimal information structure, how do we want to bias the less efficient information structure, then we use the prior, because that's then a trade-off whether A, we want to offer it, and B, in what composition we want to weigh it. But the fact that I want to be, in some sense, at the boundary or the extreme point of the convex set, for that's actually a nice point to make. That's actually true without the prior, and you would think in many situations, the data seller doesn't have a very good idea of what that prior could possibly be.
So do you have a sense of how your results might be affected if I offer the dynamic menu of experiments? So I offer one experiment, I observe the realization, then I offer another one, and so on.
It's a very nice question. No, in a sense, it's a natural question. I mean, I'm interested in dynamic problems, dynamic pricing, so it's a natural question.
Maybe for more than two states. So here's an example, right? So if you have, suppose the state consists of n binary attributes, and every type, so now there are also n types, and each of them is just missing one of the attributes. Okay.
Yep.
And so the type says which attribute you're missing. You can probably make it so, excuse me, that every type has a different valuation for not getting any further information. And now I can extract all of their value by offering each of them just the one bit that they're missing at their value.
Yep.
Right?
In some sense, you can separate the problems out along the dimension. That's right.
Exactly. And so now this is giving you a large, or a menu of size n. And it seems like you need a menu of size n.
Yes, but the type space could basically be an n-fold continuum, right? And so in each dimension, I have now a posterior whether the attribute is 0 or 1, and so therefore the type space can be much richer. And my guess is, in the example that you mentioned, again, it would suffice to basically offer for each segment a binary information structure.
Only for each segment. But so you're not claiming that you would have generally only two?
No. What I'm claiming is that generally I'm going to have finitely many. Okay, and what the bound is, that one, maybe you have to think about it a little bit.
Thank you.
Thank you.